We're going to do this example. Find the general solution of the given differential equation. State an interval on which the general solution is defined. And here's our differential equation. dy dx plus y cotangent of x equals 2 cosine of x. Okay, so let's look at it. So first of all, notice that this is linear differential equation, right? Both derivative and y raised to the first power. All coefficients depend on the independent variable x. And to proceed with this equation, we're going to follow the following steps. First, we need to put our equation in a standard form. Let me remind you how standard form of a linear differential equation, of the linear first order differential equation looks like. So standard form dy dx plus p of x y equals f of x. So if we compare the the standard form to the equation that we have here, we can notice that it's already in the standard form, right? dy dx, y with its coefficient, which is cotangent of x, and then function of x is on the right hand side, 2 cosine of x. And we need to put our equation in standard form so we can obtain this function p of x, which is the coefficient of y. So what is our p of x in this equation? Well, if this is y, then cotangent of x is p of x. Now, why do we need p of x? Well, we need p of x to obtain the integrating factor. So the integrating factor will be a factor by which we're going to multiply every term of that equation and proceed with solving it. So integrating factor. The integrating factor is e to the power integral of p of x. I'm sorry, I should have said p of x. Let me fix that. P of x dx. So we're gonna find what it is for our equation. In other words, what we need to do right now is to integrate p of x. Let's do that over here. So integral of p of x dx is integral of cotangent of x dx. Integral of cotangent of x is ln of the absolute value of sine of x. And we're not going to write plus c right here because the constant will be taken care at a later time. Okay, so let's put together the integrating factor. It's e to the power ln of the absolute value of sine of x. Right? And then now as we look at this expression, we can see how we can apply the property of logarithms here, and then e to the power ln of a certain number expression is just that number expression. So sine, absolute value of sine of x. Now before we continue with the equation itself, let's clear this absolute values, because the next step will be to take this integrating factor and multiply it by every term of our equation. So yeah, let's clear the absolute value so it's out of the way. Why do we have absolute value here? Well, because sine of x came from the logarithm, right? So it was sitting inside the logarithm. And if you remember, the domain for any basic logarithmic function is the positive number. So in other words, that expression cannot either be negative or zero. So let's think how we can clear, or how we can restrict domain of the sine function so that we can just drop the absolute value. So let's use the graph of the sine function to think about that. So the sine of the graph of the sine function is a wave, as you know. I'm gonna just put just a few values along the horizontal axis. So 0, of course, is here. Then I'll do pi, 2 pi, 3 pi. So we know that sine function equals 0 at 0, at pi, and at 2 pi. So that sine wave basically goes like this. And it continues, and of course it's on the negative side of the x-axis as well, like that, right? Continues both directions. Now, so if we want to drop absolute value, we need to only consider values of x that make sine positive and non-zero. Okay, so where is sine is positive based on the graph? Well, where we have portions of the graph showing above the x-axis, right? So right here, sine values are positive, here sine values are positive, and so on and so forth. So based on this little portion of the x-axis, I can see it's going to be between 0 and pi, between 2 pi and 3 pi, so 4 pi and 5 pi, and so on and so forth, right? So that's one. Now, because we don't want to be sine equals 0, we're not going to be including the endpoints here. But how do we restrict it? Do we use all of them, or we don't? Well, here we also have to remember that function or solution that we're going to end up with has to be differentiable. And for a function to be differentiable, it has to be continuous. So if we take only the portions, or if we keep all the portions of the graph or parts of the domain of this function where sine is positive, so all of those, well, it's going to create discontinuous function, right? To keep it continuous, I only can use one of those hills, pretty much, right? So we're going to restrict, long story short, we're going to restrict our sine function the following way. So we're going to use interval from 0 to pi. And that's basically this portion of the graph. I'm not including either 0 or pi, so I can make like holes here at 0 and pi. And that means that, well, on this interval from 0 to pi, sine values are strictly positive and the function is continuous, right? So it's differentiable, that's one, and then second, it's satisfies the domain of the logarithmic function, so I can just drop the absolute value here. So sine will stay positive. Okay, so we're going to keep this interval, and it's kind of answers the second portion of our equation, state an interval on which the general solution is defined. So far, we have this interval. If we have to introduce more restrictions, we'll find out along the way, but so far that's what we're keeping. And so I'm just going to be using sine of x from now on. So I'm dropping the absolute value. To make a note of that, this is what I'll do. I'll say that absolute value of sine of x equals, just want to make some space for me, equals sine of x on the interval from 0 to pi, like that. Okay, so let's continue. Now we're going to take this integrating factor and we're going to multiply every term of that equation by. So that's how it will look like. So it's going to be sine dy dx. Oh, I'm sorry, I skipped x. Sine of x, of course, dy dx plus y cotangent x sine x. Here I'm putting in front, here I'm putting at the end, so it would make any difference, right? Equals 2 cosine of x sine of x. So here it is, that integrating factor. That way used to multiply every term of the equation. Now, what do we have here? First of all, let's see if we can simplify anything. So what can we simplify? I think cotangent x sine x, that part can be simplified. So I'll put that on the side. Now, or maybe I'll put it here. So that's how I think about it. Cotangent is cosine x over sine x. times, that's cotangent, and then times sine of x. I can see how sines will cancel or divide out, so we end up with just cosine of x. Okay, that's how we can simplify this portion. Let's rewrite the equation. Sine x dy dx plus y. Now it just turns into, everything turns into cosine of x equals, and the right hand side, let's keep it for now as 2 cosine x sine x. Next, what we can see is that the left-hand side of this equation is actually a derivative of the integrating factor, of the product of the integrating factor and y. So let me write it down. So what I'm saying here is that the left-hand side of this equation is the derivative dx of the product of the integrating factor, which is sine of x, and y times y. Now this will always happen. It's going to happen when you solve first order linear differential equation using this method. So when you use integrating factor method, let's double check. Though. So if I find derivative of this product, well, I have to use product rule, right? So it's going to be first factor times derivative of the second factor. Well, here it is. First factor sine of x times the derivative of the second factor dy dx plus the other way around. Derivative of the first factor times the second factor. So derivative of the first factor is cosine, and then this is times the second factor. Yeah, see how it works like that? And then the right-hand side, I'm just going to rewrite sine of 2 cosine of x, sine of x. Okay, so where do we go from there? Well, here we can see that now we can apply derivative to both sides of this equation. I'm sorry, not derivatives, integrals, right? Of course, integrals. So now I can apply integrals to both sides. In other words, I can do derivative, I keep saying derivative, I can do integral. I can take integral of the left-hand side, and then I'm going to take integral of the right-hand side. Now, we know that if we integrate derivative, we just go back to the function itself. So the left-hand side gives us sine x. I'm going to put that y in the front, so I'm not confused what exactly is within the sine. So it's sine of x, but then y is just one of the factors. So it's y sine of x equals, once again, integral of 2 cosine x sine x dx. Now, once we integrate the right-hand side, we're going to obtain a solution to our original equation. How do we integrate the right-hand side? There are different ways. You can just go ahead and use substitution method, the substitution rule. Here, it's a little bit more obvious, I guess, so I'll just leave it to you to try. What else you can do here? You can use, or you can apply trigonometric identities here. So 2 cosine x sine x, it's actually one of the famous trigonometric identities. It's a double angle identity. So that expression we can rewrite as sine of 2x dx. So the one I am thinking about here is the following. Sine of a double angle, I'll just say 2a, equals 2 sine a cosine of a. So that's the identity that I applied. Okay, the left hand side is y sine x, and now that's going to be easy to integrate. So technically it's another quick substitution rule, but we know that when it's just a coefficient here, like an extra coefficient, then what we'll get is the reciprocal of that coefficient in front of the result of the integration. So in other words, it's going to be 1/2 in the front, but then integral of sine is in this at this point it's in the implicit form. If we want to put in the explicit form, we would need to get y by itself, right? Now, leaving it in that form, in this form is fine, but yeah, let's see what we can do to put it in the explicit form. To get y by itself, I would have to divide by sine of x, right? So that now the left-hand side is just y. The right-hand side is negative 1/2 times cosine of 2x over sine x. We'll see if we can simplify that using some trigonometric identities. Plus, now c1 over sine of x, it's same as what? So what is the reciprocal of sine of x? The reciprocal of sine is cosecant, right? In other words, I can rewrite it as c1 cosecant of x. And now on the side, I'm going to simplify this quotient. So let's see what we can remember from trig. We have so far cosine of 2x over sine x. Here's another double angle, right? Double angle function. We already refreshed sine of 2a identity. Well, there's one, well, actually not one, but there are 3 different identities for cosine of 2a. And I'll remind you about one of them that I think will be probably the most helpful here, because, well, if we want to cancel sine, then the one that we want to use is cosine of 2a is, let me remember, I think it's 1 minus 2 sine squared of a. 2 sine squared of a. That's one of the 3. So if I rewrite like that, 1 minus 2 sine squared of x over sine x, and then divide sine into each term of the numerator, it's going to be 1 over sine x minus 2 sine of x, right? Because sine squared of x and then sine of x, I can divide out one of the sines. So 2 sine of x. Okay, so we got that. Let's plug that into our solution. Y equals, so it's negative 1/2 times that difference, 1 over sine of x, sine of x, minus 2 sine of x plus c1 cosecant of x. I am almost out of the paper here, so we better finish, right? Y equals. Now I have to distribute negative 1/2. Negative 1/2 times 1 over sine x. Now 1 over sine x, we already talked about that. That's the reciprocal. Sine is the reciprocal of cosecant, so 1 over sine x, it's the cosecant, right? So negative 1/2 cosecant of x. Negative 1/2 times negative 2 is positive 1, so it's plus sine of x, and then plus c1 cosecant of x. And the last thing that we can do here, well, I guess second to last, I can see 2 cosecants with different coefficients. I can combine them together by factoring out the cosecant and then relabeling the coefficient. So what I'm trying to say is that I'll try to squeeze it in here and then put my final answer on the right hand side. Y equals, if I factor out cosecant, I'm going to get c1 minus 1/2 as the coefficient, cosecant of x plus sine of x, right? So those 2 cosecants I put together and I factored out the cosecant. And I was left with c1 minus 1/2. And that is the constant, right? So it's some kind of constant minus 1/2, which is a constant. So that I can relabel. And since that's going to be my final answer, I'm going to relabel it as just c. So it looks pretty. So the answer is in the explicit form, right? Y equals c. The only thing that c and then cosecant, so I have 2 c's here, but yeah, one is just the constant, and that's the cosecant. C times, maybe I'll put times, C times cosecant of x plus sine of x. And going back to the restrictions that we had for sine, remember from 0 to pi, it's up here. Remember that conversation? It's over here. Well, that's gonna end up being the interval on which the general solution is defined, right? Because that's what we had to use for sine and logarithm, right? So we'll keep that interval from 0 to pi. That's going to be the answer.